Okay, so now that we have the modeling and mapping completed for the headphones model, it's time to begin shading and texturing the model. And just some very basic definitions first, because there's some confusion about the differences between the terms material, shader, and texture. Shaders are, in essence, the instructions for how a model will be displayed. Textures are 2D images that connect to the different channels of the shader to provide visual data: color, transparency, specularity, or the highlights that appear on the surface, and bump, normal, or displacement, which provide extra information about the topology of the surface beyond the physical topology defined by the model itself. And the material is the combination of the shader plus the textures. Now, fair warning, with the possible exception of dynamics, which would be things like particle systems, fluid simulations, dynamic hair and cloth, working with materials and shaders and textures may be the most scientifically complex aspect of 3D work, at least in the sense that fully understanding how to simulate the appearance of surfaces and substances in the real world entails understanding, to a degree at least, the science behind light and even how our eyes work. Just like creating believable tornadoes or tidal waves requires at least a layman's understanding about how those forces of nature work. So I don't want to overwhelm you with a lot of what is some really dense and challenging scientific information, but we do need to discuss some basic terms and definitions because it will help you decide how to go about choosing shaders and creating textures. So the diffuse map will be the first map you paint and will likely be the easiest, or at least the most straightforward. It's also called the color map. In 3ds Max, it's the diffuse channel where you'll add your diffuse map. In Maya, it's the color channel where you'll add that diffuse map. The specular map is often the most confusing for students and professionals alike, and there are a lot of very different opinions in the field about what a specular map should be and how to go about it. But specularity is the light that is reflected on the surface of the model or the highlights on the model. So this is where we have to delve a bit into the science behind this to really make sense of what a specular map does. We only see things in the world because of light. So how light interacts with surfaces and how our eyes perceive that is due to how we perceive light. So in a very broad sense, everything we see in the world either emits light or it reflects light. It's a lot more complicated, but in service of trying to keep this simple enough that you can apply these basic scientific definitions to what you're doing, we'll try to keep it at that. We see color and highlights because light is absorbed or reflected off surfaces. The specular map defines the highlights on the model. Now those highlights will change depending on where the light is in relationship to the model and the surface quality of the model, so the light will hit the areas closest to the light first. But as you move the light, those highlights will move on the surface. So the specular map works with the lights that you have in your scene. Again, in a very broad sense, there are two types of surfaces that we attempt to simulate in 3D: dielectric and conductive. Now, don't worry about memorizing those terms. Just try to remember that conductive materials are metals like steel, copper, aluminum, etc. They conduct electricity. That's why they're called conductive. And then dielectric materials are materials that don't conduct electricity, like plastic, wood, rubber, fabric, etc. Conductive or metal materials, and for our non-scientific purposes, this would include objects that simply have a metallic finish as opposed to being made of metal, because we only care about the visual goals here and not really the scientific ones. But metal materials change the color of the reflected light. So if a white light is shined onto a red metal surface or a surface with a red metallic finish, the highlight will appear reddish. Dielectric or non-metal materials don't change the color of the reflected light. So if a white light is shined onto a red plastic surface, the highlight will appear white. So it doesn't change the color of the light. And again, these are very broad distinctions that aren't entirely scientifically complete, but just for our purposes, I want to try to keep this simple. So for metal surfaces, the highlights from the light that's reflected onto that surface will represent something close to the color of that surface. So the highlights on red metal will be reddish, the highlights on blue metal will be bluish, the highlights on gray metal will be grayish. The combination of the diffuse or the color of the surface plus the specularity of the surface produces the appearance that we see. So it's important to understand that it's an additive process. The diffuse color or the color channel plus the specular color equals the appearance of the surface that we see or that we perceive. For a metal like copper, the diffuse or the color will be something brownish orange. And this is what I have here. And this is just a free texture that I found online that's meant to represent copper. So this would be the diffuse channel. And you see that I have a layer down here called diffuse. And this would be loaded onto the color or the diffuse channel of the material in my 3D scene. The specular color for this copper will be something in the brownish or orange range as well. So you can see that I have a specular channel here. Now I just changed the color balance a little bit to make it a little bit more yellow. So the specular color is somewhere in the range of the actual color of that metal surface. The intensity and the color of the light that you use will affect that specular color on a metal surface to some degree, but for a metal, the specular color will be somewhere near the color of that metal. For non-metal surfaces, the highlights will represent the color of the light. So if you shine a white light onto a non-metal surface, that highlight will be white. If you shine a yellow light onto that non-metal surface, the highlight will be yellow. So here in Photoshop, I've set up two different files with different layers for each of the maps using these simple free textures that I found online. So one for copper and another one for wood. So for the copper, the diffuse channel has the pattern that we see in the color of the copper. It's somewhere in the orange, brown, a little bit reddish range. And then the specular channel, I simply duplicated that layer and then changed the color balance to be a little bit more yellow. Now if this were a gray metal like pewter or aluminum, the diffuse color would be gray. It may have a pattern on it as well, but it would be in the gray range. And then the specular color would also be in that gray range. To get the bump map, again, I duplicated the diffuse layer. Then I simply took its saturation all the way down to 0 to strip out the color. Now, it's important to understand that it's common in professional productions that a high-resolution model is produced that would take quite a long time to render for an animated sequence, or certainly it would be prohibitive to use in a real-time game project. So if it's Godzilla, a high-resolution model of Godzilla will be produced that has all the detail of the scales and the bumps and the veins. And then from that, a normal map is produced. And normals are the poles that stick out from the center of each face or polygon on the model that define its angles. And a normal map is produced that records every one of those normals for every face or every polygon on the model, and it's translated into a red, green, blue map. And then that normal map is applied to a lower resolution version of the model to make it appear to have all of that detail of that high resolution version of the model when it's rendered. So when the animators animate Godzilla, they work with the low resolution model, and then the normal map makes that low resolution Godzilla model appear to have all the detail of the high resolution model. For this project, you're not modeling a high resolution, high detail version of your prop. You're modeling the low resolution version and then smoothing that model to make the rounded contours more rounded. So you will be creating a normal map in Photoshop. And the way you do that is by first creating this bump map, which again is just a duplicate of the diffuse channel with the saturation taken all the way down. And on your model, you'll also be painting additional details. And the way that bump works is that middle or 50% gray, which is halfway between white and black, is flat. Black is fully concave or fully indented. And white is fully convexed or fully raised. You typically begin a bump map by using this grayscale version of the diffuse map, but you'll also paint areas of greater recession with darker grays and areas of greater protrusion with lighter grays on top of that to get better depth in the model. And then to create the normal map in Photoshop, you simply take that bump, duplicate the layer, go to your filter, 3D, generate normal map, and that will translate those grayscale values of the bump map to RGB or red, green, blue values that will then adjust the appearance of the normals on your model. And as you know from working in 3D for a few weeks now, you define the angle of something in 3D software with 3 values, X, Y, and Z. So those RGB values define the angles of each axis of the surface normal. So that pole that sticks out of the center of each face or each polygon on your model that defines the angle of that particular face or polygon can be described in 3 numerical values for X, Y, and Z, and so they can also be described in 3 values of RGB. And that's how normal maps work. But since you're not creating the high resolution model first and then obtaining the normal map from that high resolution model, this is the way you'll go about creating the normal map for your model. So I'm just going to undo this because I already created my normal map. So for the copper, I've saved off each layer as its own file. So I've saved off an image file with just the diffuse layer displayed and named that diffused. One with just the specular layer showing and named that the specular map. And then one with just the normal layer displayed, and I saved that off as my normal map. So each one of those will be its own image file. For the wood, I went through the same process for the bump and normal map. So I created a duplicate of the diffuse layer, took the saturation all the way down to get the bump map, and then used the generate normal map from the filter 3D menu to create this normal map of that bump map. But for the specular map, I obtained the complementary colors of the diffuse layer by creating another duplicate of that diffuse layer, going to the hue and saturation, and taking the hue all the way up. And that produced this blue version, which is the complementary colors. If you remember from grade school, the complementary colors. So the complement of red is green, the complement of green is red, the complement of blue is orange, the complement of yellow is purple. So the complementary colors of this diffuse map, which I got by dragging that hue slider all the way to the right, will be bluish. If the diffuse map were greenish in tone, the specular version would be somewhere in the red range, the complementary color. If the diffuse was more purple, the specular or the complementary would be something in the yellow range. And in a moment, we'll go over why we create this complementary specular layer for the non-metal materials. But here I've set up 3 planes in 3ds Max, and I've applied 3 blend materials to them, and each one has its own omnilight above its center. The first one I've set up with the copper maps. So if we go down to our maps here, I can see that I've connected the copper diffuse JPEG, which is the map I saved off of the diffuse channel or the color channel for that copper. The specular map, which is a slightly yellowish version of the diffuse layer, is the one I saved off as this specular.jpg. And then for the bump, I've attached the normal map for the copper. So if we render this, and you can see that the highlight on the surface is the color of that specular map, that slightly more yellow version of the color map. And so the highlights from the light that's reflected, even though the light itself, if I select this omnilight, you can see that the color is white. But the color that's being reflected in the render reflects the color of that specular map. And this is the basic rule for metal materials or conductive materials. Over here, I have the wood map. And for this one, I've loaded in the diffuse map, which is the color of the wood map, the specular map for the wood, which is the bluish version of the diffuse layer, and then again in the bump channel I've loaded the normal map for the wood. So when we render this, you can see that the highlight on this wood material is whitish. Now for this plane I've set up the same diffuse map for the wood and the same normal map, but for the specular channel, I've used this specular grayscale map. And just like the bump, this is simply a grayscale version or a version of the diffuse layer with the saturation taken all the way down. And if we render these two together, you can see that the one on top where we've used that bluish specular map reflects that white light. Whereas down here where we use that grayscale map, you can see that the highlight from the light is in the range of the color for the wood, this sort of brownish orange range. So why did we have to use that map of the complementary diffuse colors for the specular color of the wood material or that non-metal dielectric material? It's because white and grays are made up of all of the RGB colors, whereas black is the absence of color. White and grays are made up of all of those colors. So if we use a grayscale map or simply set the specular color to white or gray, and as we discussed, the specular color is added to the diffuse color, the specular highlights won't reflect the color of the light, but will instead reflect the colors of the diffuse map because the colors that are in the diffuse map are contained in those white or gray shades. So when you add them together, you won't get white. You'll get something that's similar to the diffuse color because those diffuse colors are already contained in those whites and grays in the grayscale map, or in the gray or white you might set as the specular color. So here I've brought both the UVW template that I obtained from 3ds Max and the UV snapshot that I obtained from Maya into this Photoshop file. And since I'm working on both tutorials simultaneously, I've brought them into the same file so that I can create all the textures that will work for both the 3ds Max and Maya versions of the headphones. You can see that the UVW map from 3ds Max and the UV map from Maya are very similar. And that was intentional so that I could use the same textures for both versions of the project. But I always place the UVWs or the UVs onto their own layer so that when I want to save off each of these different maps, I will hide them because you don't want the UV or UVW edges showing up on any of your textures, right? They're your guide for where to paint the graphics and colors and patterns and text on your color channel, and where to paint the areas of depth on the bump map. But you don't want those edges showing up in any of your textures because there aren't these green lines or whatever color you chose for your UVW edges or UV edges. Those don't appear on your prop, so you don't want them saved off in your file. So it's a good idea to keep the UVWs or the UVs on a separate layer so that you can hide them when you want to save off the files and then show them when you need to use them as a guide for where you want to paint. And then I like to create each of the maps as separate layers in the same file. You can create them in separate files, so you can have a separate file for your diffuse map, a separate file for your specular map, and a separate file for your normal map. I find it easier to do it all in the same file and just use different layers. So the diffuse channel, which is again is the color, I'm just going to take the opacity down a little bit so you can kind of see the UVs underneath. You can see that the colors I've painted line up with the UVW clusters from 3ds Max or the UV shells from Maya. So here's where that snake's head with the horn graphic appears. Down here is where the top of the cup, where it's that gray metal area, and here's where the grading will be. Here's the red areas. This is the pad on the band, which is really the only area where I have a pattern. It doesn't appear as a pattern in the color, only in the bump and specular channels. Here's the metal areas at the bottom of each cup. And these are the metal areas on the band here. These parts are the various black areas. This is the top of the band. This is the inside of each of the cups. This is the inside of each of the bands. So you can see that I've used the UVs or UVWs as a guide to where to paint things. Now I don't have any patterns in the color on the headphones. That's partly why I chose them. But if there are any patterns that appear on the prop that you've chose, such as wood grain or camouflage, etc., you would need to set up contiguous UVW clusters or UV shells for those areas, and then you would paint those patterns on the diffuse layer in your Photoshop file to line up with the clusters or shells where those patterns reside on your prop. And anywhere there's text or graphics, you would paint those on the diffuse layer to line up with those clusters or shells. So the UVW or UV template is your guide for where you paint these colors. And when you paint in 3D eventually, again, behind the scenes, you're painting onto these 2D texture maps based on the two-dimensional UVs or UVWs. Then I created a specular color layer that's the complement of my diffuse layer, another that's a grayscale of that diffuse layer for any metal materials, and then I created this bump map, which is a grayscale version, and I've created some black areas where there's some depressed lines around that graphic, one around the top part of the cup. Down here is the grading. They're sort of very depressed diamond shapes in my headphones. So because I want them to be recessed, they're black or near black. The areas around them that I made closer to white so that they appear raised. And then the name of the headphones, Be Excellent, is embossed, so it's raised lettering. So those letters are close to white. And then on the top of the band, there's this pattern of depressions. And since they are recessed, I painted them in black. And then I created a normal map of that bump channel simply by using my Generate Normal Map from my 3D filter. So for my headphones, I set up a blend shader for the plastic sections of the headphones. And I've created these as targas, as I explained in the previous tutorial. So I created a targa for the diffuse layer, which is just the color. One for the specular color, which is those complementary colors. And then I loaded a grayscale version of my diffuse map onto the specular level. And the specular level, which you can also control with this number, the grayscale map helps me control the amount of specularity. So I can adjust that map to be darker or lighter to control the intensity of the specularity. And then for the bump map, I've loaded the normal map of the headphones. Now for the diffuse and specular color, you simply click on the No Map button next to the appropriate channel, double click on Bitmap, and then load that file. And that's the same for the specular color as well. But for the bump, you have to do something slightly different. So you click on No Map, and instead of clicking Bitmap, you're going to click on the option that says Normal Bump. And then from there, and then you have two slots here. You have a normal, And that's where you'll load that normal map. So in my case, I loaded the normal map for the headphones. And whereas the normal map actually affects the normals of the surface or the way those normals appear, bump maps are fake. So they appear to have depth, but if you look at bump from the side, so if you look at these letters, if I were just using the bump map and I scrolled in and looked at the lettering here from the side, looking at it from the side would reveal that the letters aren't actually raised, that depth is fake. But with the normal map, it actually appears to be raised even from the sides. But you can use those together. So I could use the normal map for the normal slot and then the bump version for the bump slot. Now I've created a 3-point lighting scheme around my model. You will learn about 3-point lighting and lighting in general in Module 6. But in order to see the effects of the normal maps and the specular maps in particular, there has to be light in the scene. So I've set up these lights, but don't worry, you're not expected to know these for the Module 5 assignments. This is something you'll learn about in Module 6. But in order to demonstrate how the maps appear when applied to the model and rendered, I needed to set up some lights. So you'll be able to see that when I render my model, that the grading, those diamond-shaped areas seem to be depressed, and that the writing, the Be Excellent text, appears to be raised. All the areas that should be black are black, all the areas that should be red are red, and all the metal areas or gray areas appear to be metal or gray. But there are a ton of shaders to choose from in 3ds Max, and every shader has parameters that you can adjust to alter the appearance of the shader on the model. Some of those parameters will be the same from shader to shader, while some shaders will have parameters that other shaders do not. But you can experiment with different shaders and adjusting the parameters of those different shaders, as well as the texture maps, to achieve the appearance you're after. Your goal is to attempt to reflect the real-world materials from which your prop is constructed for the photorealistic version of your prop, but for the stylized version, you have a lot more leeway. But remember, if it looks right to you, it is right. So experiment with different shaders, experiment with adjusting the parameters of those shaders, using different textures for the different channels, until you achieve the aesthetic appearance that you're after. If I bring up the slate view of the material editor, you can see that there's a number of default shaders that you can choose from. If you change your renderer, so right now my render is set to render with the default scanline renderer, which is the default 3ds Max. If I change this to the Quicksilver renderer, which became standard with 3ds Max a few versions ago, and then open up my material editor again, you can see that all of these preset Autodesk materials have popped up. Ceramics, concrete, hardwood, metal, plastic. You're more than welcome to experiment with those, but fair warning, using these materials and the Quicksilver renderer will increase your render time. So depending on the power of your computer, you want to be careful about experimenting with these. Make sure that you save your work and you experiment with each one using this Quicksilver renderer before you decide to move forward with it. But you're more than welcome to experiment with any one of these pre-made materials that you want. You're also welcome to stick with the standard 3ds Max materials. So Blinn, metal, multi-layer, Oren-Nair Blinn, Phong, Strauss, translucent. Those are the basic shaders that have come with 3ds Max almost from the beginning. If you want to stick with just those, as I have here, you're more than welcome to do that. I know we throw a lot at you in this course, so if you want to stick with the basic 3ds Max materials, you're more than welcome to do that. And you can read about the kinds of real-world surfaces that those basic shaders are meant to represent in the 3ds Max help. The important thing is for you to understand how shaders and textures combine to produce materials, and how the different texture maps work together to produce the appearance of the surfaces on your models.